All right, welcome to chapter 16. We're on the kinetics chapter. So in kinetics, we are looking at reaction rates and mechanisms and all this cool stuff. So, first little section here. Reaction rates. All right, what in the world is a reaction rate? Like, what does that mean? The rate of a reaction. Like, think about it. Well, it's a rate. Rates are basically just a change over time. So when we're talking about like velocity, it's your change in position over time. The acceleration, that'd be the change in the velocity over time. So when we're doing a reaction rate, what are we measuring the change of? We're going to look at the change of concentration. So the change in concentration over time. It could be the concentration of one of the reactants. It could be the concentration of one of the products. All right, but we look at the change in concentration per unit time. That's the change in concentration of a reactant or product per unit time. Let me flip all this thing open here all at once. Cool. So the rate, concentration of A. So that A could be a reactant, it could be a product. So it's the concentration of A at time 2 minus the concentration of A at time 1. And on the bottom here is time 2 minus time 1. A much easier way to write that is delta A over delta T. Right? Delta just means final mass initial. Right? These square brackets, though, they specifically mean molarity. It's moles per liter of A. So that's the concentration that we use when we're talking about this stuff. So when you look at an equation, or not equation, but a reaction, that's what I'm trying to say. All right, so here's a picture. It shows concentration and then time. So this would be my reactant, the NO2. NO and O2 are the products. And so we start off with a bunch of NO2, and this is breaking down. It's forming NO and oxygen. All right, so this goes down. The concentration drops, and these concentrations grow. All right, and if you actually look at this, this is like kind of beyond the scope of the class, but it's just kind of cool to see. Like, look at these curves. Look at the NO2 curve and the NO curve. You can tell just by looking at this thing, they have the same coefficient in the balanced equation. And then when I look at the NO versus the O2, I can tell that the NO coefficient is probably twice as big as the O2 coefficient. So you can see this kind of stuff, and it looks pretty cool. All right, let's get to collision theory, the most complicated theory in all of chemistry. It's so horribly difficult. I'm kidding. I'm totally lying here. Collision theory, it's really easy. All right, the main idea behind collision theory is that, well, for something to react, the particles need to collide. Ta-da! All right, that's 1/3 of collision theory. So yeah, the first part is, I call it the duh part. It's like, well, collision theory, they need to collide. Duh. Beyond colliding, they need to hit with the right orientation, but they also need to hit with enough energy. So those are two other little points. All right, so yes, they need to collide, but they need to be in the right orientation, and they need to hit with enough force to cause that reaction to happen. So there's something called an activation energy. All right, so the reaction of water to form water from oxygen and hydrogen, it's exothermic. Cool, we got this, right? H2O2 makes 2H2O. All right, I can put these things in a balloon. In fact, this is one of my favorite demos. I used to like blow up hydrogen and oxygen all the time. It's really cool, really fun. Doesn't happen just on its own. You need to kind of get it to go. You need to take a match. You need to take a lit candle or something and bring it up to these guys to set this thing off. All right, hydrogen, it's got a nice, happy, stable covalent bond holding together. Same thing with oxygen. It's got a double bond holding together, so it's nice and strong. All right, we need to break those bonds. We need to give this thing enough energy to snap those bonds and then, get it motivated to form some new bonds. All right, so this initial input of energy, all right, this is what we call the activation energy. So this initial input of energy is needed to overcome the repulsion forces that occur between reactant molecules when they're brought very close together. So yeah, electron clouds don't necessarily want to, merge together, but if you give them enough energy, well, bam, all right, they will. So they need to have a lot of speed when they hit. So a match, that'll usually get this thing to go. All right, so the activation energy, this is E with a little subscript A. All right, the actual textbook definition, what you need to know. All right, it's the minimum energy required to transform the reactants into an activated complex. So what's an activated complex? We'll get to that in a couple slides here. But think of it, it's the minimum energy needed to get the reaction to go. So if I'm looking at an energy profile, a reaction profile, like you've seen, saw it maybe a few chapters ago, a while ago, it's all a blur. All right. So this is an exothermic reaction. So potassium and water makes potassium hydroxide and hydrogen, right? It's exothermic because I end up downhill over here. But now what you're seeing, this is new to you guys. This is the activation energy, right? There's this little speed bump. So you have to get over this bump. Once you get over this bump, whoosh, you go down. All right, then the reactions, it's clear sailing after that. If I were to go backwards, if I were to reverse this reaction, so this reaction is exothermic, right? It's negative 393 kilojoules. That means I am 393 kilojoules below where I started, right? It released that much energy to the surroundings. But if I run this reaction in reverse, right, then it's endothermic. Then I go uphill 393 kilojoules when I go from here to here. But the other big difference is the activation energy. The activation energy, when I'm going in the reverse direction, is the difference between here and this top dotted line, right? It's to get over that hill. Right, so much larger activation energy going reverse than there was forward. Right, this activation energy, I'm going to tell you now, it's related to the rate. Right, the smaller this bump is, the faster that reaction is going to proceed. All right, let's get to our activated complex now. All right, so when you have your reactants and they're reacting, right? Old bonds are breaking and then new bonds are forming. You go into what is called the transition state. So it's transitioning from being a reactant into products, right? There's partial bonding. So you have old bonds breaking, but they're not fully broken yet. And then you got new bonds forming, but they're not quite formed yet. You're right in between. It's like a mutant, right? So I just keep describing it as this mutant thing. It's halfway between. It's not reactants anymore, but it's not products yet. What it is we call it the activated complex, right? It's this transitional structure. Right? It's very short-lived. We can't really catch it and put it in a jar and say, look, I got a bottle of activated complex. That's really, really unstable. It either falls back apart into the reactants or it goes and just completes itself and makes products. So something like this, you get this methyl bromide and hydroxide. These react, they form methanol and bromide. All right, and right here, right at the tippy of this thing, this is called the activated complex. This is the transition state. This is where it's halfway to what's over here. So remember, in order to have a reaction, collision theory, they need to collide, they need to be in the right orientation, it needs to hit with enough oomph. All right. The correct orientation is from the back. So this is that methyl bromide, all right? The hydroxide comes in, smacks it right here. It's like one of those Newton's cradles. You know those things that you see sitting on a desk? It's like those little ball things that are just kind of like smacking around, right? It's like that. So this thing hits, and the bromine is going to go poosh, fly off the other side. All right, this would be the activated complex. So when this hits, it starts to form a bond. So this is forming. This carbon bromine bond is breaking, and it's like halfway in between. So this is my activated complex. This is my mutant right there. So it's not the products yet, but it's not the reactants anymore. All right, keep on going here. I think this is probably the last slide I'll do on this one. So spontaneity and rate. We talked about spontaneous reactions back in the last chapter. So if I have hydrogen and oxygen making water, all right, delta G is negative 458 kilojoules. So what does delta G tell us? That tells us if it's spontaneous or not. And how do we know if it's spontaneous? Just the sign. Negative delta G, that says this is spontaneous. And then I look at this, and it's also really exothermic. So it's spontaneous and really exothermic. So if you were paying attention, or this could have like slipped under the radar easily though, but I said it earlier in this talk that this could sit in a balloon. You can put this stuff in a balloon, and it's not going to blow up. It's not going to whoosh and turn into a fireball until you're ready, until you put the candle to it. All right, so delta G doesn't tell us about the rate. It doesn't tell you how fast it reacts. Like once you actually do light this thing off, yeah, it does go fast. But when they're just sitting there, it's not just going to spontaneously explode into a fireball. So it just indicates, so the delta G just indicates the natural tendency of the reaction or process to proceed. And so yeah, this definitely does have a strong will to go forward. You just need to get it over that activation energy, and then whoosh, it will go. All right, that's the end of the first one here. We will muddle our way through the next one. All right, catch you there.